Hello and welcome to the last lesson, and what a nice short presentation this is. We're primarily looking at some meanings and using our calculator and a chart, or rather stat crunch and a chart. First of all, a scatter plot you're probably familiar with. It's a data collection point, so it looks a lot like just plotting points in algebra. When we're dealing with it from a statistical purpose, then these values are not just values, but they have meaning. So what we see here is that the years of education are on the x-axis and the score on a test measuring prejudice is on the y-axis. Now, it appears that as the years of education increase, then the scores go down. Do not mistake that and think that in any way education causes that. It may play a role in it, but so does just the increase in life experiences. If people have more years of education, they have more experiences and interactions with other people and just learn more about the world at large. And so it's not just the education role. So we're never saying that correlation implies causation. We're just saying that they're connected in some way. Really, then we would say that because these are kind of headed downhill along the way and they're almost in a line, then they're correlated. But correlation does not imply causation. Now, we can measure correlation with a correlation coefficient R. R is like slopes, so we've done some algebra earlier in the class, and the slope of a line, the closer it is to 1, the stronger the regression is. Okay, we're not going to calculate the equation for the regression line. You want to learn how to do that, take stats. But what we know is that lines that kind of go uphill from left to right have a positive slope, and lines that go downhill from left to right have a negative slope. So in this case, we're going to talk about positive correlation and negative correlation. A regression equation shoots through kind of the pack of points, and it's trying to hit as many as possible, but just kind of go up through the middle. So if I started here at 0, 0 and shot through that pack, what we would see is I'd have a positive correlation. But this one would be pretty moderate, maybe even on the weak side, because those points are not really closely packed to the line. However, this one, the slope of this line would be negative, and these are almost lined up exactly. So this would have a really strong negative correlation. On this one, we get a pretty strong positive. This one is a kind of a fairly strong, not nearly as strong as B, but it's a fairly strong negative. Now, E is essentially a perfect positive correlation, and F is no correlation. There is no reason you wouldn't know if you needed to put that line headed up or headed down or headed sideways. No correlation there at all. The R value, though, the closer it is to -1 or 1, the stronger it is. So we can look at this R value and calculate it without graphing all of these points and just trying to eyeball and say, well, I think it's moderate, or I think it's fairly strong. The closer, since it can go to -1 or 1, the closer the absolute value is to 1, the stronger the correlation is. Now, there is a formula for calculating the correlation coefficient, but we don't want to do it. There is a way to do it on the graphing calculator, but in this case, you don't want to do that either, because you would have to type in all of the points, and unlike some problems, you can have quite a few points this time. So the easiest way for us to do this correlation coefficient in this lesson is to use Stat Crunch. Stat Crunch, when you've got a listing of all the values, there's a little icon beside it, and when you click that, the very first thing you see is a dialog box that asks you, do you want to open it in Stat Crunch, copy it to the clipboard, or open it in Excel? Choose Open in Stat Crunch. It's going to take all of those values and import them into 2 columns. The X values in the first column, the Y values in the second. And then you want to go above where it's imported them in. So like right here, you can see that variable 6, there's nothing in it, but that's because way over on variable 1 and 2, there were things in there. You're going to choose Stat. It's going to open up a drop down, go to Regression, which will open up an additional menu and choose Simple Linear. So open in Stat Crunch and then go up above the numbers, find Stat, Regression, Simple Linear. Once you click Simple Linear, you get a new dialog box that opens that has a lot of choices, but you don't need to fill everything in. If you only need R, then the only thing you need to do is the top two options, which will say X variable and Y variable. And you're going to do a drop down, and you will see a listing of phrases there that correspond to the meanings of the variable. Like on our previous slide, we talked about years of education and then the test score. And so those would be your options when you do the drop down. When I was doing this sample here, my options, you can actually see them in the results. After you click those two options, choose compute. Then you will get a display that's kind of like I've got here. And you can actually read what I put in. This was to see if there was a correlation between people who do not approve of marriage equality and will not try sushi. The sample size was 4, so it's a ridiculously small sample. It also is kind of ridiculous to look for the correlation like that, because who even cares if you do or don't try sushi and what relation that is to not approving of marriage equality. But at any rate, at the bottom of this display, or I don't even know if it's at the bottom, you just look closely and you're going to have R, because there may have been more that I cropped off, I can't remember. But R is your correlation coefficient. So even though it would be ridiculous to say not approving of marriage equality causes you to not try sushi, we can see that we have a really strong positive correlation coefficient. Okay, really, really strong. Do keep in mind, just like I said, there were only 4 on that previous one I did. If the sample size isn't large, that coefficient correlation can be totally misleading and ridiculous. So statisticians have developed a way to determine whether correlation is likely to really exist. We can't say for sure, but if correlation is likely to really exist based on sample size. This has a bit to do with that law of large numbers also, because again, the more you include in the sample, then the more relevant the results actually are. What we do is N is the sample size, and this little symbol here is alpha. It has to do with the probability that the variables are not actually related. If we have an alpha of 0.05, that means there's a 5% probability that the variables are not actually related. And alpha is referred to as the significance level. This chart is not a complete chart, and you cannot find this on your calculator. Maybe it is in the back of your textbook, I think, but the easiest thing you're going to do is just when you're working a problem, you will have a link you can click to open up the chart. So you'll click that link to open the chart. That chart is where you get a critical R value. It's kind of like where you're going to draw the line, and then we're going to see if we're past the line with the R value our problem gives us. So in this particular case, on this suppose, it says suppose N is 10, and it says and alpha is 0.05. So you're going to go down this column and over, and we're going to connect right there. The critical value then is 0.632. Now, we're wanting to use that critical value, and what I have here in bold is kind of an important key point for you to remember when you're doing your homework. If the absolute value of R is greater than the critical R value, then you'll say correlation exists. So as I look at this absolute value, it doesn't matter since this one's positive, but this is the R value from the problem. So the absolute value of that is 0.62. The critical value I had was 0.632. And in this case, you want to figure out which one of these is bigger. Well, 0.63 is bigger than 0.2. So does correlation exist? No. Correlation does not exist, at least for alpha of 0.05. That means you're trying to make a 95% probability of being correct and only a 5% probability that they're really not related, so we would say no there. But alpha is not set in stone at 0.05. They can give you any alpha value that they want to. Let's do another problem. Suppose N is 15. So if N is 15, we're looking at this row, and it says alpha is 0.065, that's ridiculous. Okay, we're going to change that because I believe that's a typo. How about that? Watch how I can change a typo. It's like magic. We're going to say 0.05. Okay, they're going to give you an alpha of 0.05 or 0.01 or 0.005 or something. It'll be something on the chart. You're not going to have a number like 65. It's not on the chart. So here I've got alpha is 0.05. So again, I'm going down this column. So the critical R value I'm looking at is 0.514. Okay, this is the R from the problem. So this one's also positive. Now they could be negative. That's why I'm always saying you got to look at absolute value. But the question is the comparison between the R from the problem and the critical R of 0.514. So here, R is larger than 0.514. Does correlation exist? Yes. Correlation does exist at the alpha is 0.05 level. So at a 5% significance level, correlation exists. Well, what if they decrease that significance level to 1, where we only want a 1% chance that we're wrong? Well, if we're only going to do a 1% chance, that means I have a different R value, okay? Because instead of using this 0.514, I need to do my comparison to 0.641. But now my R value didn't change. So in this case, though, 0.641 is bigger than that? No. We would say correlation exists at a significance level of 0.05 or 5% significance, but it does not exist at 1% significance. Because again, it depends on how sure you need to be that you're correct. And so this would be 99% sure I'm correct, or 99% probability I'm correct, really. And then this one would just be a 95% probability I'm correct. So if you decrease alpha, it kind of raises the bar on whether or not you're going to say correlation exists. Okay, so let's look at a particular homework problem then. Here, it's kind of blurry because I just copied and pasted, but this was a homework problem. And then I clicked to open the chart, and so see, this is what it looks like. So going through this problem, the correlation coefficient is given, and n is 10, and alpha is 0.05. And that's very common. It doesn't have to be 0.05, but again, that's common. Now notice, even though this is in multiple columns, it's really one long chart. They only gave me the 0.05 for this, but I have lots and lots of n values. So n is 10. I only need to go to here because if I go any further, I've moved over into n is 42. So my critical R value is the 0.632. I'm wanting to compare the absolute value of R to the critical R. And if it's greater than that, then we would say yes. Now I've already checked that so that you can see as it is, because they gave me, if I put the absolute value of 0.75, I do get 0.75. And that actually is greater than the critical R I've circled over here of 0.632. Again, if this was an R value of 0.8, it would be a stronger correlation. But we do see that the correlation does exist, and so you just click that. So if the absolute value of the R from your sample is greater than the critical R from the chart, you'll say yes. And that's the end of this lesson.